okay? So a one-to-one function is a very mathy definition up here. It says f of x is one-to-one if you have elements a and b, so like basically your x values that are in the domain of f, where a does not equal b, implies that f of a does not equal f of b. What does that even mean? Yeah, let's think about this in terms of just a picture, okay? Basically, what it is saying is if I have a graph, this pen is way too large. If I have a graph, okay, and let's say I just had like a line. If I had just a line on my graph, what it's basically saying is that I don't want to have two values that have the same y output, okay? So like if I look at this horizontally, is there only one y value for every x value on this line? Yep. Yes. So instead of the vertical line test, we're going to use this thing called the horizontal line test to test whether or not functions are one-to-one, okay? Now we're going to do a little flashback to geometry today. Do we all remember that? Yeah. Geometry. Do you guys remember logic statements in geometry? What? Like if, then, and then reversing it. Do you remember the word contrapositive?
Oh, that's right, like flip it into the things and the other, yeah.
So we're going to use the contrapositive, okay, in order to show that a function is one-to-one, okay? So basically doing like a little mini proof, okay? Those were not over in 8th grade. Okay, so this is the the contra positive. Okay? Now, this is not something that you are going to like need to know for a quiz or a test, but it's good to test our strength and test our knowledge. Okay? So the contrapositive basically just says I'm going to take the opposite, or I'm going to negate this statement of a does not equal b, which means f of a does not equal f of b. So I'm negating that, which is saying a equals b, therefore f of a equals f of b. Okay? So I negated both of them. So now we're going to show whether this function is one-to-one using that negation. For example, a, okay? So if I look at example a, what I'm going to say is I want to let a equal b, and I want to show that f of a is equal to f of b. Okay, so we're going to let a equal b, and we want to show f of a is equal to f of b. So what I'm going to do is I'm just going to plug in a where x is, and I'm also going to plug in b where x is, and I'm going to set them equal to each other, okay? So we're going to set negative 4a plus 12 equal to negative 4b plus 12. Okay, if I solve this, 12 go away. I'm left with negative 4a is equal to negative 4b, which if I divide by negative 4 on both sides, I end up with a equals b. Okay, so we have just shown, yes, that this function is one-to-one. So f of x is 1-to-1. We can also think about this, well, negative 4x plus 12 is a line, right? So yes, again, this is kind of showing why, showing a little mini proof. On your homework, you're going to have a lot of, you're given this function, is it one-to-one, yes or no? Look at a graph, basically, okay? All right, and then on this one here, letter B, okay? If we do the same thing, we're going to end up getting that, yes, it works. However, there is a counterexample for this one, okay? Do you guys remember proof by contradiction or proof by counterexample from geometry? No. It's when you give an example of something that basically tells it that it's not true, okay? So basically, if we think about plugging in a value for x, okay? First of all, does anyone know what this function looks like? Square root of 25 minus x squared. We talked about it last unit. It's not exactly just a shooting star graph. It's actually a half semicircle, okay? Because I've got that x squared. If I plugged in, let's say I let x equal 3 and x equal -3. If I plug in both of those values, I get f of 3, which is equal to the square root of 25 minus 3 squared, which would equal square root of 25 minus 9, which is square root of 16, which equals 4. When I plug in -3, am I going to get the exact same thing? Yes, I am. Okay? So basically, we just proved by contradiction that even though, I'm going to kind of write this out here, even though our A value and B value don't equal each other, our f of A value and our f of B value both equal 4, right? Which if you go back to the first definition here of a one-to-one function, if we have something A and B don't equal each other, the function at that value is also supposed to not equal each other, right? But we just showed that they are equal to each other. So therefore, those 3 dots mean therefore in math. It's a notation. Okay. F of x is not 1-to-1 by the definition. Okay, so basically what we just did is we found 2 values that are not equal to each other, 2 x values that give us the same y output, right? Because I kind of just told you this graph here actually looks like a semicircle. So at 3 and at -3, those values for the y are going to be the exact same, and they're going to be 4. Okay? So, proof by contradiction. On your homework, all you're going to have to tell me is it a one-to-one function, yes or no? Okay? Yes, Will. All right. So then the horizontal line test, we kind of talked about this already, but the horizontal line test basically just says if it intersects more than one y value, then it is not 1-to-1. So I'm going to kind of do this first one with you, and then I'm going to let you try out the last 4 by yourself. But basically I want you to decide whether it's a function or whether it's a 1-to-1 without the use of a calculator. So we need to remember how these functions look. Okay, we need to remember transformations. I want us to draw a sketch of each one of these. So if I was drawing a quick sketch of letter A, right, I know that's going to be what kind of shape? A line, right? And it's going to start down at -5, and it's going to have a slope of 2. Now, it doesn't have to be perfect, but a nice little sketch of what that looks like. Okay? Then I know if I drew any horizontal line all the way up, it is always going to give me just one y output. So yes, this is a 1-to-1 function. It passes the horizontal line test. All right, so take a few minutes right now. Try out B, C, D, and E, graphing those functions. Just a quick little sketch, and then identifying whether it is 1-to-1 or not, looking at the horizontal line test. And then check with people next to you. Okay, your graphs don't have to be perfect, but we're just going to kind of go through this here quick. Letter B, -2x squared, that's going to look like what? An upside down parabola stretched by 2, right? So, will this pass the horizontal line test? Nope, it does not pass. Not 1-to-1. Okay. Letter C, 2x cubed minus 1. What's that one look like? Goes, yep, the little kind of S thing here, but it goes straight up, straight down. However, technically it's shifted down 1 with a stretch of 2. Will this pass the horizontal line test? Yes, it will. Yes, 1-to-1. Absolute value. What does absolute value look like? It's a V. Yep. Technically shifted where? Shifted up 2 and right 4, but technically that's not going to really affect our 1-to-1-ness. Is this 1-to-1? Nope, it does not pass the horizontal line test. Not 1-to-1. And lastly, I've got the cube root of x minus 3. The cube root, very similar to the cubed function, except for it is down here like this. And shifted where 3? Shifted right, technically, because it's with the x there, okay? So technically that shifted right 3. Is this 1-to-1?
Yes.
Yes, this is 1-to-1. Okay? Now, quick question for you guys. All odd degrees. Are all odd degree polynomials or functions going to be 1-to-1? Yes. What about all of my even functions?
No.
My even functions are not. Okay? So that's kind of a hint for you guys when you're going through your homework. All right, next page. Okay, we're actually talking about inverse functions now. You guys talked about these last year, I do believe. Okay, what is an inverse function?
You replace like the x with the y.
Yeah, you like flip the x's and y's, right? Okay, if you guys remember in geometry, right, if I had a graph, technically the inverse is graphed over the line y equals x. Oops, y equals x. Okay, so whatever function you have, you are taking it and you are flipping your x's and your y's over that line to get your inverse function. Okay, that's like kind of the visual way behind what's happening. So now in order to show that a function is an inverse function, we have to do this. We have to show that f of g of x is equal to x for every x in the domain, and g of f of x is equal to x for every x in the domain. There's a lot of words there, but basically we just have to show these two things. So for example 3 here, we are taking our f of x, which is equal to x cubed minus 1, and our g of x, cube root of x plus 1, and we're plugging in those values. Do you guys remember how to do that? If I said g of f of x, or f of g of x,
Yes.
do you remember? Okay, good. It is not fog of x. It is f of g of x. Okay, no one's going to say fog out there, right? Just like no one's going to say sin of x or cos of x in this class, right? Ever? Tangent, yes. Okay, so I am doing f of g of x, which is the same thing as f parentheses g of x, okay? We are taking our value of g of x, this thing right here, and I am plugging it in for what? Where am I plugging it in for the function f of x? I'm plugging it in for x, okay? So we now have y equals the cube root of x plus 1 in parentheses to the third power minus 1. All I did was take what that g of x equals, and I plugged it in just for x, right? And now we can evaluate this. The cube root and the cube, that's going to simplify out, right? So I've got y equals x plus 1 minus 1, right? Technically, I don't even need these y equals, actually. I'm going to erase these because we're just evaluating this function. It should give us x at the end, which it does because x plus 1 minus 1 is equal to x, okay? Now, if the other one also equals x, then we have shown analytically, or like algebraically, okay, that these are inverses of each other. So, for the second one here, I am doing g of f of x, not gof of x, g of f of x. The same thing as g parentheses f of x. Okay, so now this time I am taking my f of x function, which is x cubed minus 1, and what am I doing with that? Plugging it in for x in my g of x function, okay? So now let's just go ahead and write this out. I've got my function is the cube root of my x value is now x cubed minus 1, and then I've got that plus 1 there. And then I can simplify that Negative 1 plus 1, that gives me just 0. So the cube root of x cubed is equal to x. Okay? So therefore, right, we can say since f of g of x and g of f of x both equal x, f and g are inverses of each other. Now, for example 4, it says decide whether each equation defines a one-to-one function. If so, find the equation. Okay? So it's kind of one of those things we got to check and see, is this going to pass the horizontal line test before I just go ahead and start switching my x's and y's and solving for the inverse. Okay? Also, last year, did you guys talk about this notation? Yes? That stands for the inverse, right? That is my inverse function because f of x is my regular function, right? F to the negative 1 of x does not equal 1 over f of x, okay? Just because there's a negative x, that is not the same thing, okay? It just means that you're switching the x's and the y's, and this is your inverse. So I want you to get in the habit of, if you're actually solving for an inverse, I need you to write it as f to the negative 1 power of x. Okay, I will take points off if you do not. Okay. Okay, so looking at example A here. First of all, think about what this looks like. 2x plus 5 is it's a line. Okay, so since this is a line, does this pass the horizontal line test? Yes. Passes horizontal line test. I'm just writing a little note here because we did do something before. Now we're just actually plugging in our values. Okay. So now we can do the little algebra that is going to take not a whole ton of effort, but switch your x and y values and solve for y. I like to start by writing y equals because it's in terms of f of x, which is fine. And then I'm going to switch my x's and y's to give me x equals 2y plus 5. Okay, which, quick little math, subtract the 5 and divide by 2. So I get y equals x minus 5 divided by 2. Now, if you left your answer like this, I would take off some points because, to me, this just looks like an equation. This is actually an inverse, so I needed to note that it is an inverse. So I need to write f inverse of x is equal to x minus 5 divided by 2. Okay, also, when we're thinking about switching our x's and y's, okay, in terms of domain and range, right? I'm going to write a little note over here on the side. In terms of domain and range, domain is all of your x values, right? Range are all of your y values, right? So if I'm switching my x and y values for my inverse, what also switches technically? Your domain and your range, right? Which, when we're talking about like lines or anything to like an odd power, it's really not going to matter because if I have a line, right, the domain and range are both going to be negative infinity to infinity, right? Same thing if I had like a cubed function, right? Domain and range are all going to be negative infinity to infinity, okay? It gets tricky when we talk about what we're going to see in example 5 when we have square roots, okay? But let's first look at letter B. Letter B here, I've got y equals x squared plus 2. What does that function look like? A parabola, okay? Does that pass the not vertical, but horizontal line test? Nope. So not 1-to-1. Therefore, okay, no inverse function. Okay. Go ahead and try out letter C. Decide whether or not it is 1-to-1. And then find the equation of the inverse and make sure you write it as an inverse, not just y equals. All right. First of all, is this 1-to-1? cube function, right? It's just shifted to the right 2. So yes, it is 1-to-1. Okay, so I'm going to switch my x's and y's. So I've got first y equals x minus 2 cubed. That was a terrible 3. And then x equals y minus 2 cubed. Now, a few people in this class and last class did this. Just distributed the 3 there. Can we do that? No. Same thing if it was squared, right? If it was squared, I don't just distribute it to each of those terms, right? You're technically taking this thing and multiplying by itself 3 times. But I would not do that if I were you. I would just get rid of the cubed. How do I get rid of the cubed? Cube root it. So I get the cube root of x is equal to y minus 2. So that means that y is equal to the cube root of x plus 2. Which we need to rewrite this as the inverse function is equal to that thing. So that I know this is my inverse function. Okay, example 5 is finding the inverse of this function again. However, we have to consider the domain and range because what does this function look like? We talked about this last unit. The square root of x plus 5. Yeah. Yeah, the shooting star, right? So if I drew a little sketch here, it's the shooting star, but it is shifted left 5, right? So technically it looks like that, yes? Okay. Remember when we found domain and range of this function? I would set that x plus 5, the stuff underneath the square root, greater than or equal to 0. Or if you look at your graph, you can tell that x has to be greater than or equal to negative 5, which written as an interval would be negative 5 to infinity, correct? What is the range of my function? 0 to infinity. Okay. So is this function 1-to-1? Yes. Horizontal line test, it passes, okay? So we need to go ahead and find the inverse of this function by switching my x's and y's. So I've got my original here, switching my x and my y, and solving for y. So I'd get rid of the square root, square both sides, and I get that y equals x squared minus 5. X squared minus 5 looks like what? A parabola, okay? So this is my inverse function, okay? Because the function was 1-to-1 originally, right? This is my inverse function. However, there is a restriction on it. Okay, so if I were to graph this, let's graph this really quick. The actual function of x squared minus 5. If I were to graph this, that is a parabola starting down at negative 5, right? And it would look something like this, correct? However, that does not pass the horizontal line test. So there needs to be some sort of restriction on my domain, right? My domain has to be greater than or equal to 0 because that is what my range is. Okay, the range now becomes your domain for your inverse function. So my domain is now 0 to infinity, and my range is now negative 5 to infinity, okay? So if I were to redraw this, technically, that is what your inverse function looks like, okay? Just the blue piece there, the black piece there is your regular function, and this blue piece is your inverse function, okay? Does the domain and range make sense in terms of that picture now that you can see it, okay? Lastly, just like when you talked in geometry about reflections, right? We're reflecting it over this line, y equals x. So whatever point I have over here, which is negative 5, 0, I'm switching my x and y values to now become 0, negative 5, right? You're technically switching the x and the y values for every single point on your graph. Last thing about just kind of your important facts. I'm going to draw a little picture here for you, okay? I've got my f of x function and my inverse function. Okay, this is your f of x. This is my inverse function. Okay, so important fact number 1 is if the function is 1-to-1, then the inverse exists. Okay, that's your first thing you got to check. Then the domain of f, so if I have my domain here, that is equal to my range in the inverse. The range of my function is equal to the inverse domain. And the last point there says that if I have a point A, B, so like if this point we labeled was A comma B on our graph, then on the inverse function, that point becomes B comma A. Okay, and just like I said on that last example we did, the graphs of f and the inverse function are actually just reflected across the line y equals x. Okay, so there will be a few, I think maybe like 2 or 3 questions on your homework where you just have to graph the function and the inverse function together on the same graph so you can see that they are a reflection of each other. Okay. All right, we got 3 examples left of the exponential functions, and then you guys got the rest of the time to work on your homework. So, we have seen these before. Yes? Yes. Exponential functions. How would you solve letter A without using logarithms or anything like that? You flip the things next class when we talk about logs. We're not flipping anything this class. We're using algebra rules of exponents, okay? So what we are going to do, this is basically the only note that I would say to write down here, is you are going to set each side to the same base. If we have the same base, then that means the exponents have to be equal to each other in order for that equation to be true, right? So 25 and 125, what can I have the same base be? 5. So this becomes 5 squared raised to the x power. 125 is 5 to the 3rd power. Okay? Well, if I have a power raised to a power, that's the same as multiplying. So I've got 5 to the 2x is equal to 5 to the 3rd. And now, if I know that they have to be equal, the bases are the same. So I just set the exponents equal to each other. So I now have 2x equals 3, which means x equals 3 halves, yes. Okay. Is it coming back? Kind of, yeah? Okay. There will be some on your homework that have base of e. Don't freak out. Just use your exponent rules. We're not doing logarithms or anything, okay? It's just set the base to be the same, set the exponents equal to each other, okay? Letter B, I've got 1/3 and 81. How do I want to make same base here? Do we want to use 1/3?
No.
No, I wouldn't. Let's use 3. How could I change 1/3 into 3? That would be 3 to what power?
Negative.
3 to the negative 1 is equal to 1/3, yes? Okay. And that is technically raised to the x power. And then what is 81? 3 to what power? 3 to the 4th. Okay. Now I can multiply these. I've got 3 to the negative 1x is equal to 3 to the 4th. So I set them equal to each other. Negative 1x equals 4, which means x equals negative 4. Okay. Last example here, letter C, 1.5 x to the plus, or sorry, to the exponent of x plus 1. And then I've got 27 divided by 8 to the x power. How could I rewrite 1.5 to be a fraction? 3 halves. Okay. So 3 over 2 to the x plus 1. Could I rewrite 27 over 8 in terms of 3 over 2? Probably. But it would be to what power? To get me 27. 3 to what power gives me 27? 3, right? So 3 to the third power gives me 27, and 2 to the third power gives me 8, right? So they're almost quite the same. I got to take that 3 out on the right-hand side. So I've got 3 over 2 raised to the x plus 1 is equal to 3 over 2 to the what power? 3x, right? And now I've got the same base, so I just set my exponents equal to each other. Quick little algebra here. X plus 1 equals 3x. So 1 equals 2x, which means x equals 1/2. Okay? So get your bases to be the same, and then set your exponents equal to each other. Okay?